panelists. If no one
Yeah, we'll
else
still wait for a bit of it.
wants to kick it off. Yeah. We can get started. My question is about something that Karina brought up, the universality of thermodynamics, and I'd like to hear what people had to say about that. Do we actually think it is absolutely universal? And let me motivate that question. A while ago, we had a reading group where we were reading David's papers on black hole thermodynamics, and I find myself wondering, well, why is there a subject such as black hole thermodynamics? And David makes the case that black holes are indeed thermodynamic objects. And if there's a case to be made, it's not everything's a thermodynamic object. Black holes are things, therefore black holes are thermodynamic objects, right? It actually takes some work. And I found myself wondering why there's a subject of black hole thermodynamics rather than a general subject of thermodynamics of self-gravitating systems, of which black holes are a special case. And it seems to me that there are two ways it could go. One could be, there could be a general thermodynamics of self-gravitating systems and things get simpler when they're black holes. Or it could be that only certain kinds of systems with maybe certain kind of symmetry properties can be treated as thermodynamic systems. And so would it be absolutely devastating if we took the latter approach? If we decide the latter, and except in special cases we can apply thermodynamics only when we can treat gravity as more or less negligible. So I was wondering hear what you guys think about that.
Yeah, I mean, there's lots of bits in that question. I think it's very hard to defend the claim that you can't use thermodynamics and statistical mechanical reasoning except where gravity is negligible, just because we use statistical mechanical and thermodynamic methods all the time in astrophysics. I mean, if you're interested in nuclear fission, or if you're interested in how long it takes white dwarfs to cool down, you're interested in instability timescales in globular clusters. There is an enormous literature of the application of statistical mechanics and thermodynamics in self-gravitating systems. So if you're not allowed to use thermodynamics and statistical mechanics in that case, then somebody needs to tell several thousand people in the astrophysics community, and I don't actually think they're going to be very impressed by being told that. But as far as black holes are concerned, I mean, I suppose put it this way, and I'm not sure this touches on the universality issue so much as on black holes. I mean, a lot of what the thermodynamics and statistical mechanics of black holes has turned on is, well, if black holes are just like other self-gravitating or non-self-gravitating systems can be treated as unitarily evolving quantum mechanical systems whose dynamics is reversible in the usual unitary way. If that's the case, then the fact that there's a thermodynamics of black holes is unsurprising, and the fact that it has some of the odd features it has just becomes a special case of the thermodynamics of self-gravitating systems. But of course, at first glance, you wouldn't think that black holes are ordinary quantum mechanical systems of that kind, because it looks as if information crosses the event horizon and doesn't come back again. So I think that's the place in which you might think, okay, even if you've got a general case for universality of thermodynamics, you might think, well, at least as long as you're trying to do physics outside the event horizon, then black holes ought to be an exception to that case, because you've got this irreversible loss of quantum information across the horizon. And from that point of view, that's what makes it so striking that that doesn't seem to be the case, that the black holes do seem to have thoroughly statistical mechanical properties, although of course that's contentious. I suppose the other side of it is it's quite surprising to be able to find the derivations of black hole thermodynamics at such a phenomenological level. So the fact that general relativity seems to reproduce this thermodynamic description isn't something you'd expect from the shape of general relativity. I mean, we don't, by and large, it's not as if you get out the thermodynamics of stars just by the analysis of general relativity. You have to put in rather more than that. So that's the other side, I think, that's so surprising there.
Yeah, I think also the fact that with black holes, we're talking about a space-time region. We're not talking about a box of gas or or a star. So I think it is quite surprising that we can do stuff with a black hole or with the event horizon. So I think we should be very much surprised at the laws of thermodynamics apply there.
Yeah, I think this point that it's actually a space-time region we're talking about is actually quite funny, because there's no actual skin that you come up against, a bam, hit on the edge of the black hole and go, there it is, touch it, not be able to come out. You pass through the event horizon, it's just empty space, unless there's a firewall. So it's weird to attribute thermodynamic properties to a space-time region as such. That is strange. I mean, there's also kind of, it's funny that I think all three of us do agree that black hole thermodynamics is really thermodynamics, and we're all on that position, but because we've got to the point of actually being able to understand why. I mean, if you look at the history of the subject there, when black hole thermodynamics, Bekenstein first proposed it, if I'd have reacted to that, I would have said, no, that's not thermodynamics, that's just an analogy, that's something that's got formally similar structures, but it's not thermodynamics. With the advent of Hawking radiation, their game changes. And of course, the Hawking radiation is not just gravity, that's gravity plus quantum field theory, or gravity plus quantum mechanics to get Hawking radiation out. And that makes it actually a genuinely thermodynamic object, and you can do things like you can actually start considering, as Karina has done, putting a black hole in a Carnot cycle as a working substance in a Carnot cycle, and there it's not analogy, its identity. You actually have an intraconvertibility between statistical mechanical systems outside the black hole and the actual supposed thermodynamic properties of the black hole. And then at that point, as far as I'm concerned, it's game over. It's thermodynamics. Prior to the Hawking radiation and prior to the arguments about that you can put that into a Carnot cycle, I would be going, no, it's just an analogy. It's just a nice form of analogy that might be useful.
I mean, I think I mostly agree with that. I mean, just as a qualifier to that, or to what Karina said as well, I mean, relativists tend to define black holes as space-time regions. That's the definition you tend to run into if you read Wald or something. And that's the definition that tends to flow into the philosophy of physics community. But astrophysicists don't tend to talk about black holes that way. Astrophysicists will say one black hole is orbiting around another, this black hole used to be oscillating, but now it's oscillating less than it was, this black hole was formed at such time. I mean, those sentences aren't even grammatical if black holes are supposed to be space-time regions. And so there are other uses of black hole in the physics community which much more talk as if a black hole is a spatial region. And I think a lot of the point of the membrane paradigm in the 80s was to, by putting a skin around the black hole just outside the event horizon, even if that skin is invisible to the person who falls into the black hole, one way of thinking about that is it gives you the conceptual resources to describe the black hole as a sort of an object that evolves on time-like paths and actually can have changing properties. There was something else I was going to say that I can't recall. The only thing I was going to say was, so it does require quantum field theory, of course. It doesn't require matter to do this. I mean, if I just take low-energy general relativity and I treat it as a quantum theory, then I can do Hawking radiation through graviton emission. It's not like I need electromagnetic fields or scalar fields or something.
So I would say one thing that it also has, and it's this: there's something about it that I still find very puzzling and very perplexing, and I don't know if anyone can help me with. But I'm very happy with we take what we understand about black holes as objects sitting from the outside. In the description, we've got Hawking radiation. What I don't know, and this is one of the things that I still, as far as I understand, is still a matter of debate, is we can now look at that as an object and say it's got these thermodynamic properties. Okay, great, happy with that. But we don't necessarily have a very clear statistical mechanical derivation of those properties from statistical mechanics itself, in the way that we have our statistical mechanical model of an ideal gas, a statistical mechanical model of a van der Waals gas, statistical mechanical models of semiconductor physics, where we've got the actual fundamental physics and we derive the properties. And it's not obvious to me that that's there are lots of different routes and lots of different things and very high-level arguments, and it's not clear that there's actually a particular statistical mechanical model for
I think we do have it and we don't. I mean, there are some things we have that are different bits of the elephant. I mean, I think if you do that low energy quantum gravity thing I was talking about a moment ago, you just treat general relativity as a quantum field theory and assume it's cut off at the Planck scale. If you work out the black hole entropy that way using ordinary statistical mechanical methods, so just work out the partition function and then calculate the entropy from it, you get back out the Hawking result, the Bekenstein-Hawking entropy, and you do better than that actually. You get it out for rotating or charged black holes. If you add higher derivative terms to the Lagrangian, then there's a modification of the Bekenstein-Hawking formula, and you get the same modification out on the statistical mechanical side. So I think that's really powerful evidence that there is a statistical mechanical description there. Having said which, G appears in the formula for the Bekenstein-Hawking entropy. It's the renormalized value of G. In a quantum field theory like general relativity as a field theory, then that value is controlled by the short distance physics, and it's exactly that short distance physics that we don't know. So we sort of know that provided that there is a sort of consistent quantum gravity theory that has quantum general relativity as a low energy limit, we've got really strong reason to think that theory will indeed produce the quantitatively correct stat mech, but the actual nature of those degrees of freedom is completely hidden at that level of description. And then you've got much more you've got fragmentary stuff in string theory that depends on your take on string theory, but is quite difficult to interpret. You've got argument if you use the sort of more modern techniques of ADS-CFT duality, and you say, well, look, a black hole in a box is this is desperately hand wavy, but a black hole in a box is like is dual to a conformal field theory on boundary of that box. Then again, you can work out the entropy using that conformal field theory. Again, insofar as you can do the calculation, which you can qualitatively in some cases, quantitatively in others, you get out the right answer. But again, that map between the conformal field theory and the black hole degrees of freedom is obscure and badly understood at exactly the point at which you'd like to understand what the black hole degrees of freedom are. So I think there's really good evidence that the black hole does have microscopic degrees of freedom, but the theory, and that they work out quantitatively right, but the theory makes it very hard to see what they actually are.
And of course in LPG you have the number of spin number things that are
Yeah.
in LPG there's some exponential.
Cool. So that side of it I don't know anything very much about. I know the sort of string theory route to it, but yeah, I understand that there's almost a sort of universality here, which I guess is what you'd expect from the quantum field theory side of it. So if the quantum field theory tells you that any consistent UV completion of GR as a quantum theory ought to reproduce the statistical mechanics data because we've done that in low energy, we get it out. So insofar as loop quantum gravity is a consistent ultraviolet completion of quantum general relativity, we'd expect it to get that, and conversely, to some extent, the fact that we do get it out, I guess, is some kind of consilience evidence that LQG really is a consistent theory. But I don't know much at all about the nature of black hole stuff there.
Put that to the test. And I'm going to go easy on you to begin with. So, something evocative in your talk, which was that principal theories explain nothing. Does that mean that Einstein's principal theory of special relativity did not, in any sense, explain the null result of the Michelson-Morley experiment in your view?
Well, I am prone to hyperbole in my talks, if I think it'll get a laugh. Yeah, I am generally sympathetic to the argument that, say, Harvey Brown has put forward in the last decade or so on this issue of principal versus constructive theories in relationship to special relativity, and that indeed Einstein himself endorsed later on in life, was that that principal theory formulation of special relativity was, all well and good, but in the end, for an proper explanation of why the Lorentz transformations hold, you need to have a theory of matter that gives you dynamical laws that behave in the right kind of way. So that kind of dynamicist in the terminology of that particular debate on special relativity, that kind of dynamicist account is certainly more appealing to me. than the principal theory of closure. And that does go through with most other things for me. As I said about the sort of the thermodynamics, it's one thing to say, yeah, if your phenomena show these particular properties, and you suppose that these particular sets of properties or things are always going to be the case, then certain other things are necessarily going to follow, and you can say certain things are necessarily going to be true about any kind of dynamical laws that underpin it. So in the case of special relativity, you can say, well, if the dynamical laws are Lorentz invariant, then Einstein's principles of special relativity will hold. If Einstein's principles of special relativity will hold universally, then the dynamical laws must be Lorentz invariant. And for me, the arrow explanation there is the physical laws explain the higher level phenomena. Because it simply could have been true that the dynamical laws were different, in which case those higher level phenomena wouldn't hold. Whereas it's the fundamental laws that ground everything. And that follows through for me in statistical mechanics as well, and all other various other things. So any kind of principal theory or symmetry property, you go, well, why does this hold? Because the dynamical laws are so. And it's true that given some particular high level set of principles, that's not enough to necessarily fix what the physical laws are. There's lots of different laws that are Lorentz invariant. It doesn't tell you what they are, but it's the fact that the laws were Lorentz invariant is the thing that does the explanation for me.
And in this case, it's presumably something like it's the fact that the laws are reversible, or volume conserving, if you like.
One of the reasons why the interesting thing for me about trying to pursue this program of adding fluctuation phenomena to the higher level principles is to try and actually bring, there's now quite a closeness now between how we can understand the principal theory of special relativity and how we can understand the dynamical approaches. And we can see how they fit together very nicely. Yeah? One set implies Lorentz invariance implies the symmetries. Great, goes backwards and forwards. We don't seem to have a grasp on what the fit is between phenomenological thermodynamics and statistical mechanics, and maybe it would be helpful in our understanding of it if we actually brought the two together. So one of the exciting ideas, that's one of the motivations for adding fluctuation phenomena, is to try and actually make thermodynamics look more like statistical mechanics so we can understand what it is that's special about our laws that make them the case. And I think our laws are more special than they need to be. So there's actually a lot more to our laws. There's a lot of extra symmetries to Hamiltonian dynamics, both classical and quantum. There's more there than you actually need just to get kind of a consistent phenomenological with fluctuations thermodynamics. The property I think that might be doing most of the work is measure preservation. It's a measure preserving map.
That's what I had in mind for reversibility, though I said it's too bit crude. Yeah.
So if I can push back on that, I'm curious to your response. To my mind, saying that it's Lorentz invariance as the fundamental model that explains things is not proven in any way that constructive theories are offering explanations. Because to my mind, it's just another way of expressing the principle. So if I can derive the null result of Michelson-Morley experiment from the light postulate and relativity postulate, and then I say, look, it doesn't matter whether your constructive theory is made out of particles or fields or strings or what have you, as long as it satisfies these principles, i.e. it's Lorentz invariant, this will follow. So I don't need any of the details of the constructive model. All I need, the only constraint I need to say about it is that it satisfies these principles. That's what's doing the explaining. And this transition from, to just say, referring to the constructive model. Oh, here's this constraint on the constructive model. It satisfies the principle. Therefore, the explanation now goes under the column of the constructive model's accomplishments. Strikes me as just crazy because it relies on none of the details of the constructive model that you're aiming for. So Einstein, was I think right to say that a better explanation would be a full constructive model because that would explain so much more. But ultimately, to explain the Michelson-Morley experiment, he didn't need all the details of the constructive model. It wouldn't help him have those details. Those extra details would help explain the rest of it and maybe fit things together. But it still seems to me that it's the principles that are doing the explaining.
So I don't have a dog in this fight, but just to try to separate it out. So I can see two claims one can make. One could say, look, the constructive piece is something like the realization that the theory has Lorentz symmetry. You could also say, look, the constructive piece is the full standard model of particle physics. I mean, which is I'm not quite sure which.
Whether it's particles, strings, fields.
Well, I guess I mean, look, that actual model. I mean, we don't think that's fundamentally true, but one thing you could have been looking for in a constructive model, constructive theory, was some kind of general constructive dynamical principle like Lorentz invariance. Another thing you could be looking in for constructive theory is that actual theory. So, I mean, there's at least some sense in which it feels like what Einstein had in mind was more something like the standard model rather than the principle that the theory has Lorentz symmetries.
Right. Or a symmetry that's respected by a model set strikes me as a principle, right? Like I can start my model construction exercise by saying, I'm going to impose these symmetries. And now there's still lots of possibilities for what model I might construct. But ultimately, I'm encoding the principle that this is a symmetry of nature as a constraint on my model construction. I'm still, and if I can explain something just by saying it has that symmetry, and not by referring to any of the details of the models, that strikes me as a principle-based explanation.
So here we've got our ambiguity over what constitutes a principal theory as well, and that's one of the things in this whole separation between principal and constructive theories is that it's not a category distinction. It's the actual question of what makes something a principal theory is itself a bit fuzzy. It's just something Einstein actually made up in order to try and explain what he was doing. And so one of the debates in the special relativity literature is about, which is the right constructive thing? Is it the dynamical approach where it's the dynamics and the laws, or is it space-time geometry? Is it the geometricist view? The space-time geometry view says space-time has a particular geometry to it. It's this Minkowski space-time. And it follows from what it means to say that space-time is Minkowski, that any physical processes in it are going to have to be Lorentz invariant. Now, that is, within the literature, presented as actually being a constructive explanation. A geometric construction is contrasted with a dynamical construction view. But equally, people have said, maybe that's actually a principle view, because it's a principle that's being put forward. So I think that, there's a point at which I'm not actually terribly sure there's much of it at stake in the argument as to is it a constructive or is it a principal theory, and which should we do? I'm not actually as strongly committed to being opposed to constructive view. I mean, I use a constructive approach when it seems to be helpful to do so. I guess what it comes down to then is the much bigger argument of what constitutes explanation. For that, I simply go, I refer you to the philosophy literature, and good luck to you.
Well, heaven helps you.
One way to make it precise, what question should be answered, is that you can have a debate about methodologically what would be the most useful way for us to proceed to make discoveries. So one position would be, we should build more models. We should commit ourselves to a particular ontology of the world, work out the consequences, and try lots of possibilities, and that would be the way to make progress in physics. And another radically different point of view is, no, we should focus on what sorts of principles we should encode in any model, and what follows from those principles, regardless of the details of your model. And so I would certainly argue that we have too little of the second thing in physics today, and we need more of it. And I would use Bell's theorem as a great example of something that we have today that's led to an immense amount of progress, and it's independent of the details of the model. It just says, if your model is locally realistic, I don't care what manifold of invariable states you carry. That is irrelevant to the argument. This will follow. And I feel like we need more of that, but perhaps you think we need more of the first thing. That would be one way in which you could be championing constructive theories over principal theories as a way of making progress.
I would actually say I don't feel I am championing principal theories over constructive theories in anything like that level of strength that we require to commit to it. If it's pragmatically useful and heuristically useful to actually take a constructive theory approach, by all means do it. Don't stand in the way of progress. You're free in the context of discovery to use any heuristic you wish.
Being a little mischievous, I think there are important ways in which modern quantum field theory is a principal theory in the way you're discussing. One writes down very general claims about its symmetry structure and then gets most of the rest of it out.
both would agree with each other. I mean, look, on this, on the point of that paper, was recovering electromagnetic theory without the ether. And that's what did it. And what role, I mean, where does the details of doing that come in your stories about how it worked? Or what was successful about it? I mean, clearly, if you hadn't done that, it wouldn't have, you know.
I'd say my understanding of this is really informed by the kind of the Brown.
Sorry, I couldn't.
My understanding of this is so heavily informed by the Harvey Brown analysis of it that, you know, I'm just basically going to present Harvey's story on this, was that Lorentz and Poincaré were actually taking Maxwell's equations as given and deriving the relativity principle from it as an explanation of Mitchell's and Morley thing. But Einstein in 1905 didn't have that option available to him, because Einstein in 1905 almost uniquely believed in the existence of photons. So Einstein couldn't rely upon Maxwell's equations as being the fundamental theory. Now actually, Lorentz and Poincaré didn't believe in Maxwell's electromagnetism as the fundamental theory because they knew that there weren't stable bodies in Maxwellian electrodynamics. So they also knew that there had to be a new theory coming to replace Maxwellian electrodynamics. But Einstein was already seeing photons as being something that actually undermined Maxwellian electrodynamics, so he just didn't see that constructive approach as being available to him. And in desperation, therefore, he gives up the constructive possibility because he doesn't know what the fundamental theory is to build it from, and adopts the principal theory approach as a sort of a policy of despair. Interestingly, Gibbs justifies in 1902 in his preface statistical mechanics, principle of statistical mechanics, developing his view on statistical mechanics in almost exactly the same kind of grounds, because Gibbs refers to the fact that we don't have a good theory of atomic theory. We don't actually know what the thing is, and there's various problems that are currently unsolved, like diatomic gases should have 6 degrees of freedom, but our measurements only can identify 5 degrees of freedom, so there's something wrong there. And of course, quantum theory was also the solution to that.
Everyone's being frozen out because it's too low energy or something.
Yeah, exactly. So Gibbs effectively adopts a much more general, higher level thing, even though the statistical mechanics looks more like a constructive theory to us now. But in a sense, he was doing a similar kind of move, stepping back from a specific model and working on high level principles. But that looks like a constructive model from our current way of trying to carve things up into constructive and principal theories. So, you know, I think that these distinctions are actually really just a lot more fluid, and we adopt whichever one seems to be pragmatically useful, and I'm happy if people can find something pragmatically useful. I think ultimately, though, I am a scientific realist in that, I'm not a constructive empiricist. Fine, take advantage of everything available in order to define constructual models, but in the end, the justification of them, of the success of the scientific theories, comes on down to it's because they're capturing the structure of the way the world is. And I'm going to stake that flag and die by it.
Yeah, a historical footnote that did this. Einstein's answer to Bill's question, we could put his fingers, well, what's missing from that 1905 paper that doesn't that would be required to actually have an explanation? Well, Einstein formulated the principal theory construction theory distinction when asked to write something for the London Times about the special relativity, and so that that was actually formulated to answer Bill's question. And his answer is, well, in the 1905 paper, I just postulated the light postulate and the principle of relativity, and just presumed that rods and clocks were going to behave in such a way that you couldn't distinguish states of motion. Sort of what's missing is a constructive account of the behavior of rods and clocks in terms of the dynamics of their constituent parts that would have the consequence that they do behave that way. And Einstein, because Einstein himself says, we only understand something when you've got a constructive theory. So basically that that distinction was formulated for Einstein to explain what he thought was missing in 1905. Yeah.
David, no, so I have this vague recollection of reading a quote by Fermi. I'd be happy if anyone knows this, but it's on your point about field theories being, in a sense,
Yeah.
something like, prior to Einstein, physicists would construct models and then work out what their symmetries are. And after Einstein, physicists posited symmetries and built their models with that symmetry as a constraint.
I didn't know that.
That's a nice quote. Yeah.
But I think I mean, from a QFT point of view, it's I think it's really after Wilson, people and after the whole rethinking of renormalization, that puts you in a position where you think that once you know the symmetries, there's not much else to say, because the theory. The symmetries tell you the form of the equations of motion, or the Lagrangian, up to the value of coefficients that you expect to be set by higher energy physics that you don't have anyway, and so you treat as phenomenological. I mean, again, if I was continuing from mischievous, you can think about the whole naturalness principle here as just being that kind, pushing forward that kind of way of thinking, and the sort of the current crisis of the LHC, I think, is showing that method's stopping working in ways that we really don't understand. But yes, I was agreeing with something actually. So this is something I could have asked for your talk and didn't think to later. I mean, the crucial difference, well, a crucial difference at least, between what Lieb and Ingwersen are doing and what's going on in the resource theory framework, is the difference between saying this is thermodynamics regarded as autonomous, how it was being done in the 1800s, and this is thermodynamics regarded as the control theory of an antecedently understood theory. I mean, what do you think, this is meant as a rhetorical question, what do you think we should be getting in 2018 out of the sort of entirely autonomous account of thermodynamics?
The Lieb and Ingwersen.
Yeah, or more generally that way of thinking about thermodynamics, where we're just silent on the underlying macrodynamics.
Yeah, I'm not sure. I mean, I'm not sure we can get up that much. I think it's a neat thing to show which mathematical assumptions go into your entropy function. But I'm actually quite concerned. Well, I'm not concerned, but I'm not sure about the physical usefulness of the Lieb and Ingwersen approach to thermodynamics. If that makes sense.
Makes sense.
Yeah. Mainly because we know thermodynamics is wrong as well.
Well, here we go. No, that seems
well,
to be wrong.
the orthodox second law is at least is being violated on a regular basis.
Oh, you mean the principle that is exceptionally impossible to... Okay, yeah, fair. But I guess the other thing I don't know enough about for that kind of approach to thermodynamics, I mean, it's one thing to say, okay, my thermodynamics is such that my external parameter is the volume of a box or something, and I'm moving a piston. I mean, I don't know enough about how much the Lieb and Ingwersen approaches and their variants generalise to situations where, let's say, my external parameter is magnetic field strength or something like that.
I'm not sure. I haven't come across that. To be honest.
I mean, I guess your first half of your talk is a partial answer to the question as well. I mean, insofar as we've got a route from the fluctuation story to constrain the microphysics, then the two are closer than they look.
Yes. Sorry. Again, I missed part of your question. You were asking Karina, so I'm not quite sure.
Oh, I was asking about how we should think about the foundational status of entirely autonomous constructions of thermodynamics, like the Lieb and Ingwersen approach or Kara-Theodori's, in the present era where we actually have an underlying framework for dynamics. So there's a big difference between the Lieb and Ingwersen approach and the sort of control theory approaches that have been sketched at various points in this meeting, is that the latter are very much the control theory of an antecedently specified dynamical theory, whether that's classical mechanics or quantum mechanics or whatever, whereas the Lieb and Ingwersen approach is kind of an axiomatization of 19th century thermodynamics, which is just silent on what the underlying theory might be, or even if there is an underlying theory.
Yeah. Yeah, I mean, I suppose, yes, the first half of my talk is an attempt to try and bring them into SIG, or closer.
Closer contact, please, yeah.
Closer contact. The question that can be asked of the approach. It's the old-fashioned Carnot cycles approach. Is it possible to add fluctuations to the Liebenian basin approach? And good job for someone to try.
I guess sorry, can you?
No.
One thing that makes me a little sceptical of some aspect of the Liebenian approach, not as mathematics, it's very, very attractive from that point of view, but as a framework is, as I understand their framework, quite a lot of the work that their axiomatization does and quite a lot of how it moves beyond Carnot is it gives me a sort of characterization of the topology of the equilibrium state space in terms of the accessibility relations, whereas in Carnot-Theodori's approach I just kind of posit that there's a state space and it's structured like a manifold or whatever. But of course, if our starting point is that the state space is underlied by the classical or quantum state spaces, then we get a huge amount of topology for free without needing to give an operationalizing of it.
You should know, that Liebenian basin have tried to, I don't know if it ever got published, but I've seen talks where they've tried to generalize their approach to irreversible phenomena.
Yeah, they do that.
Which, although they were seeing it as generalizing its non-equilibrium, and they just sort of took for granted that meant irreversible.
I see.
So, because I look at the Liebenian basin approach and I say, I don't see anything that means there's necessarily equilibrium in here. It's just that it's taken for granted that if you're out of equilibrium, you must have irreversible processes. They just put those two together. And it's not clear to me that axiomatically that should be the case. There's also, if you drop the comparison hypothesis, there's interesting generalizations that go along with it. If you drop the comparison hypothesis, you get it turns into a partially ordered set of states, and then you have a family of entropy functions. Yosefink actually points out when you drop the comparison hypothesis of the Liebenian basin approach, there's actually a theorem in economics about rational preference choice where you have a partial order of preferences that's exactly turns out to be the same as the Liebenian basin approach, which is quite interesting. So again, those axioms, there is an issue, like somehow these do pop up in other situations. But what do you make of that? What I make of it is mathematical structures have multiple applicability.
Sure. Sorry. I was going to just come back on the point of Karina's. It occurs to me maybe...
Well, has a finger on that.
Maybe I want to push just a little bit back on the kind of, the traditional understanding of the second law is just wrong. In one sense, obviously you're right. The thing that was being written down in the 19th century was just wrong because they thought it had probability or something. If you were thinking, okay, what's the right way to interpret what we now mean by thermodynamics? It's not at all obvious to me that we shouldn't be just interpreting that subject as being a subject about expectation values. If thermodynamics means the thing that practicing physicists call thermodynamics, well, that's obviously already hugely vague because it's used in such different ways. But if you try to say what's that bit of contemporary physics discourse which is the most natural successor to the thing that was called thermodynamics in the 19th century, it's not at all obvious to me it shouldn't be described in terms of expectation values.
You say it should, or
it should be? It's not at all. Let me strip some negatives out. It seems to me reasonably plausible that it should be described in terms of expectation values, at which point it continues to be exactly true.
Oh, I completely agree. And I find it still puzzling in the physics literature that people adopt different versions, and in the philosophy literature as well, different versions of the second law. They restrict it to different systems of different sizes. Some of them talk about the statistical second law that's sometimes violated. Others say, well, the second law is never violated, and so you always have to read between the lines which second law they're actually talking about. But yeah, I agree. Like the working law is definitely the probabilistic one.
I'd like to say a little bit about, in response to you raised the point about expectation values and why is it that we've got the laws of thermodynamics that seem to be very successful, and then when we go to statistical mechanics, it's expectation values of things that are actually going to turn out to be what the thermodynamics was supposed to be referring to. And again, there's a great quote which I can't trot out quite so easily in Gibbs's preface about this. It's great, you should read Gibbs's preface. It's got lots of good insights into it. In which he says thermodynamics is what holds for situations where we don't have the ability to actually see minor deviations or the resources to repeat our measurements so many times that we can see the deviations from the mean. So what he's saying there is thermodynamics is the set of laws we get in situations where we expect the expectation value from our measurements.
Nice.
And of course, yeah, if you're in a situation where you expect the expectation values, then you'll get expectation values in your measurements. And if you have very sharply peaked distribution, so in all the situations where thermodynamics holds, it had better be the case that when we apply statistical mechanics to it, the statistical mechanical probability distributions are ones that are sharply peaked around the mean value. And guess what? If you've got large numbers of bodies that consist of large numbers of atoms, nice combinatorial arguments suggest you will expect the expectation value. Great, so that's why thermodynamics works.
Cool.
But statistical mechanics gives us so much more. It gives us probability distributions where you don't expect the expectation value, and you can still use them, and we can use all the apparatus of probability theory on those situations, and get much more results out.
I suppose I think I agree with all of that. I was thinking even about the thermodynamics of the 19th century as Gibbs is coming onto it, let alone current thermodynamics. I almost think this is like a semantics of interpretation point. I mean, so 19th century thermodynamicists established that there was a property U of systems, and a property S of systems, and a property V of systems, and there was a W thing you could get, and a Q thing you could get, and they had a bunch of mathematical relations connecting them together. Now, to some extent, it's up for grabs whether we want to say, well, they were correct to think that the U was mechanical energy, and wrong to think that the mathematical relations held exactly, or whether we want to say, well, they were right that these mathematical relations hold exactly, but they erroneously thought that W was the mechanical work done rather than the expected value of the mechanical work done. And at some level, there's not going to be a deep answer to that question. I mean, whenever you've got some mistake of that kind, you've got a bump under the carpet you can move around. But there's at least a productive way of reading even 19th century thermodynamics that says that what they got wrong was they slightly misidentified what work was, rather than they slightly misidentified the relations in which work stands.
Actually, Rob had a finger up a while
I have
ago,
a finger too. On this
you put a finger up, Rob. Do you want to?
Yeah. What do you think?
Okay.
I guess if I may be indulged, I just want to read that paragraph from Gibbs that Owen was referring to, because it's actually very lovely, and it actually speaks precisely to this point about principal constructive theories, even though. Okay. So the laws of thermodynamics, as empirically determined, express the approximate and probable behavior of systems of a great number of particles, or more precisely, they express the laws of mechanics for such systems as they appear to beings who have not the fineness of perception to enable them to appreciate quantities of the order of magnitude of those which relate to single particles, and who cannot repeat their experiments often enough to obtain any but the most probable results. The laws of statistical mechanics, on the other hand, apply to conservative systems of any number of degrees of freedom, and you're right, conservative means volume conservative, and are exact. This does not make them more difficult to establish than the approximate laws for systems of a great many degrees of freedom or for limited classes or things. The reverse is rather the case, for as our attention is not diverted from what is essential by the peculiarities of the system considered, and we're not obliged to satisfy ourselves that the effect of the quantities and circumstances affected will be negligible in itself. The laws of thermodynamics may be easily obtained from the principles of statistical mechanics, of which they are incomplete expression, but they make a somewhat blind guide in our search for those laws. This is perhaps the principal cause of the slow progress of rational thermodynamics, as contrasted with the rapid deduction of the consequences of its laws as empirically established. To this must be added that the rational foundation of thermodynamics lay in a branch of mechanics of which the most fundamental notions and principles and the characteristics of operations were alike unfamiliar to students of mechanics.
And then he goes on to talk about diatomic molecules on the next page.
Yeah. So, you're right.
What I'm trying to play on is this discussion of comparison hypothesis and
That was obviously trolling, mate.
Let me give you an example of something that I think it has caused. So if you just focus in on Liebman-Nicholson and comparison hypothesis, they give some justification for it in terms of citizens and axioms. As you point out, if you drop it, then you can get a partial order. But just knowing that isn't knowing much, because you might ask, well, when does it hold? When doesn't it hold? So this modern framework of resource theories has answered these sorts of questions. So one thing it does for you is it makes a very clear conceptual divide between types of state conversion. So the basic ones that people in the community talk about are deterministic state conversion, catalytic state conversion, where you're allowed to borrow a state but you have to return it at the end. That's like having a cyclic process. Asymptotic state conversion, where I have many copies of the state. I can go to many copies. That's like the thermodynamic limit. Stochastic state conversion, where I don't have to do with the probability one. And in each case, you can ask, what's the partial order that's induced by free operations? And we can work out that, in the theory of atonality, or non-uniformity, for example, for asymptotic conversion, it's a total order. Comparison hypothesis of Liebman-Nicholson holds. But for deterministic conversion, it is not a total order. So they're just wrong. It would be wrong to assume comparison hypothesis there, so it doesn't hold as a theorem. Similarly for analytic conversion. So in fact, what you find when you look at these theories is that the holding of the comparison hypothesis is the exception, not the rule. It's only in very limited circumstances that you expect that total order to hold. That's something we didn't know before. I think that's real progress.
Yeah, that's fine. That's fair enough. I mean, I think David really got it right. If I didn't put my hand up, nobody was going to put my hand up. So somebody had to. But fair enough. Actually, no. Results theories does produce interesting results. I fail to see it as a founding structure of statistical mechanics. In that sense, I feel that there's already a good structure for the kind of statistical mechanics, and results theory, is an interesting set of results that fits within that. But for me, it doesn't seem to be that's telling me how to understand statistical mechanics. It's interesting results that fit within statistical mechanics that I already have. But you know what? If you discover new results with that, then that's new results that are discovered using that, and that's good and fair enough.
Well, it takes an analogy. One can be, we talked about this last night, one can be really impressed by the Jasinski equality in thermodynamics without thinking that it's improved our understanding of the foundations of the subject.
Yeah.
Michael, you can...
This might actually go nowhere, but so it's kind of directed at Yoss, who isn't here. So I was wondering if people might speculate on. So he mentioned during the talk that he, when he gave the story of quasi-universal processes, going to Tatiana Erifat's he wasn't able to convince John Gordon. But he didn't mention why.
It's a special case of more general principle.
I was wondering if anybody.
Well, okay, so let me, I can speak to that because that paper by Norton was published in Studies in History and Philosophy of Modern Physics, and I was the handling editor. And it includes a section about I think the simple answer is that once John gets an idea in his head that someone else is wrong, he has a habit of reading other people uncharitably. And in fact, I think there are early drafts of the paper on the Phil Sci Archive where I think he's demonstrably unfair to the authors that he's quoting. There's a way. Like, he quotes various textbooks and things, and there's a way to read those things as sort of gesturing more or less elliptically towards the account that he gives, but they just don't spell it out. And there's a way to read the textbook accounts as being, just idiotic. My own view is that he's not reading America's, how do you say that?
Tatiana.
Tatiana. He's not reading Tatiana as charitably as one ought to. But yeah, so if you're interested, it's in the paper. There, in John's paper, there's a section about her work and why he doesn't think it quite
So
solves the
you
problem.
would disagree with Yosa's characterization of what she's doing, and that matches up with what.
He disagrees that it matches up as well with what he was saying as Yost presented. I actually had it up here. Yeah. So. Talk about something else. Okay.
Josh wanted to come in.
Oh, I thought, so I'm sure it's like you further just confirmed my classes, but I thought the problem was that John's thought that these quasi processes that Josh was talking about are somehow outside of this, nonetheless are kind of still actual processes. And so, he just runs this line before either that. Either they move or they don't.
Either they, sorry, I can't hear it.
Oh,
Yes. Either they what or they don't?
either they move or they don't. So I take these quasi processes that are supposed to play this kind of, they're not part of the sense of this. And but nonetheless, I think John says these that somehow we're supposed to understand these things as being actual, and then once you say that, then I take it all of things spoken about it, pushing that, but this is just remembering, so.
And in his general discussion of these quasi-static processes, I think there's a sort of danger of proving too much here. I mean, sure, absolutely. If you are guiding the system from, say, a low volume state to a high volume state quasi-classically, and you're doing it by really slowly moving the volume of the box, then sure, of course, in the asymptotic limit, if you don't move the box volume at all, then the box volume doesn't change. And sure, there's never going to be a speed at which you can move it that's so slow that there's literally no entropy rise. But of course, if you, in the spirit of the resource theory conversation, if you have much finer control of the system than that, if you have such fine control of the system that you can just turn off the Hamiltonian, turn on a Hamiltonian if you desire, let the system evolve under that Hamiltonian, and then turn it off and turn the new one on again, then sure you can evolve the system in entropy-preserving ways. You can do it as fast as you like. And there can't be some general result to the effect that it's never possible to transform a system from one equilibrium state to another equilibrium state without increasing entropy. That has to involve some additional constraints of the of the control operations available.
So I got the thing up and can I just read what he says? So he prevents Tatiana's view, and then there's a section that says about the problem. Quasi-static processes as iterated equilibria are real processes unfolding in time. They depend on just the troublesome notions we have seen in other treatments. The states through which the process was passed are not equilibrium states, but they are so close they are as good as or well nigh. So a lot of people invoke things like, okay, you're doing this so slowly that it might as well be an equilibrium all the time, something close to it. And he says, well, we don't have a clear understanding of that. But then his own account is a sequence of processes which get closer and closer to the equal to this equilibrium curve. So, my own opinion is that if you apply the same critical standards to Norton that Norton's applying to other people, you can advance the same kind of criticism. So, fortunately, the processes are said to proceed infinitely slowly. And a lot of people say that, and I think, by the way, this is for all you young philosophers out there. When physicists say infinitely slowly, or when they say something is infinitesimal, it almost never means what you think it means, right? When philosophers hear the word infinitesimal, they think, some quantity that's greater than 0 is smaller than every rational number. Whereas when physicists mean it means it's so small that its size is negligible relative to some other scale relevant to the problem. There's a great sentence in Tolman's book on statistical mechanics. He says, let's divide the volume of the gas into infinitesimal volumes which are large enough to contain many molecules. That sounds. It's the philosophers who are laughing. Physicists aren't laughing. The physicists are going, why does that sound funny? Right? And actually, one of these days I'm going to write this. I think that when physicists say infinite, they really mean a zillion in a technical term introduced by Sean Levine in a nice book several times. A zillion is something that's so big that it doesn't really matter how big it is, right? Right? So if someone says, well, why don't you buy a Learjet, right? I might say, well, they cost like $1 zillion, right? I mean, I have no idea what it costs, right? I just know it's way beyond my means, right? Right. So, anyways. So some of the people that Norton quotes and criticizes talk about processes that happen infinitely slowly or happen in infinitesimal increments. And John points out correctly that if you really mean it goes infinitely slowly, then it gets stopped. It's not doing anything, right? The process is never completed. A process that takes infinitely long to complete is a process that doesn't complete. But Tatiana, says actually, and I'm reading a quote from her, which is in Norton's paper. Of course, an exact infinitely slow process does not exist. Hence, one cannot say that the just described arbitrarily slow process has an infinitely slow process as a limiting case. And so far, that could actually be a quote from John Norton, right? If we still apply the name infinitely slow to the just described process, then we need to say thereby that the process at issue is sufficiently slow that we may neglect thereby certain deviations in the state from equilibrium states. So John doesn't like that. There's a further problem arising requirement that processes jump successively from equilibrium state to nearby equilibrium state. In generic systems, no single jump can complete if it is to terminate in the equilibrium state. Informally, as the process approaches the equilibrium state, the driving forces drop to 0. The result is, at least in the generic case, that the approach is asymptotic, coming arbitrarily close to completion, but never arriving there in any finite time. Okay, yeah, well, fine, but my response to that, yeah, so again, let the thing be arbitrarily close to, so close to completion that it doesn't matter how close. And then he gives the example of a body, heat flow between two bodies of different temperatures, and if you apply the heat equation, then the temperature difference decays exponentially to 0. It's not, and it never reaches it. Okay, yeah, but you can get so close it doesn't matter.
While we're at it, sorry, go.
What's that?
No, I was going to say briefly, while we're at it, at infinity means 2 or 3 times as far away as the relevant interactions, and isolated means nothing is close enough to mess with its internal dynamics very much.
Yeah, that's absolutely right. So, to my eyes, if you can read what Tatiana's account and Norton's account, and if you gave me a job of who said it and had a passing from one to the other, I would probably have difficulty saying it. John is reluctant to acknowledge that what she's saying is as close to what he was saying as both Yost and I think it is.
By the way, just one random observation picking up on this thing about quasi-static processes. I mean, one thing Wayne and I were talking about earlier is how, at least inside ordinary thermodynamics, leaving aside the more sort of small system quantum cases Rob was talking about, it's really surprising how little interesting difference there is between what you can do with arbitrary fine control of a system and what you can do with the relatively coarse tricks of changing bulk parameters really slowly. So, I mean, to pick an example from my talk, the Carnot limit governs how much work you can usefully get out from an energy transfer between heat baths at different temperatures. If you have absolutely complete control of all of the microphysics of the whole system, you still can't exceed the Carnot limit. If you have a box of gas and you can pull a piston into it and out of it, and you can do it as slowly as you like, and if you can put that box of gas in thermal contact with things, you can get as close as you like to the Carnot limit. It's kind of striking. Your intuition, I think, would be that the extent to which you increase your control resources so dramatically from these incredibly crude moving of pistons to completely fine-grained control of the Hamiltonian would give you a comparably dramatic increase in your thermodynamic resources. And it's kind of striking, at least again, in the sort of expected value game and at least in the classical large system case, how small the gap is and how little you really get out from that level of fine control. Mm.
English language sentence, having access to micro degrees of freedom, is a bit ambiguous when we try to formalize it. There's two possibilities for what that could be. On the one hand, let's take the classical case that you were discussing, you say, I can do any symplectromorphism on the total phase space of these n particles.
Yeah.
On the other hand, it could be, I can prepare a point distribution on the phase space of these n particles.
Yeah.
Now, if you ask, well, what's the sort of resource value of those things? Well, being able to do any transformation, but you're still stuck with things that are closer to thermal, for example. That ultimately is the distribution that you have in terms of how much work you can access. But if you take it in the second sense, that, I can really prepare a point distribution, which in many contexts that's what people have in mind.
Yeah.
Then the amount of work you get out of that is tremendous.
Of course, yeah. No, effectively you got zero temperature from that and you do what you like. Yes, no, I absolutely agree. But I think also interestingly, giving this comes into sort of Maxwell, Diemann, Landau's principal issues, but giving yourself the ability not just to manipulate the system, but to use that manipulation so as to gain information about the system, that won't do you any good either, as long as that information gaining process also has to be physically modelled in a larger framework. But yeah, I agree. If you're just handed by an oracle extremely fine-grained information about the system state, and if you also have extremely fine-grained controllability, then yes, of course, that gives you enormous capability you didn't previously have. I don't know who's officially running this, but is that probably a good point to...
So, actually, David, what you just said, so even if you have complete fine-grained control over you manipulate the system, you can't violate the Carnot limit. Now the picture, correct me if I'm wrong, so the picture is you distinguish between the system and various heat baths that you can interact with.
Yeah.
And are you assuming canonical distribution for the heat baths, or?
In the thing I've stated, then yes, I am.
Right.
But if you sort of want to blur it out a bit more, you can imagine, I'm Maxwell's demon, I've got superfine controllability and things. Some new system turns up, and I don't at this minute know very much about it because it's a new system. Then even though, so claim, but I think this is right, new systems turned up, I don't at this moment know much about it. Even though Maxwell's demon, even though I have the measurement capability if I want, to learn as much as I like about its microstate, and even though I can manipulate that microstate to an arbitrary degree, it's still the case that I can't do that much better than much simpler systems of getting energy out, because even if I use my superpowers to measure the system, ultimately my measurement and implementation process is instantiated in a larger unitary or, as it were, symplectic transformation, and so I'm still paying.
The whole system consisting of original system plus the heat baths.
Plus me, plus wherever, plus my memory, yeah.
Okay.
And then it's one of these nice calculations you can do that if the demon's got some spare memory, then yeah, absolutely, the demon can carefully memorize the information about where the system is and use that to get useful work out. But the demon actually could have done just as well to run an ordinary kind of Carnot type heat process between system and its memory. All that careful measurement isn't doing you any good at all.
Yeah. In possession of a memory that's in a special state, throw away the box and just expand your memory isothermally, and you get the same amount of work out.
Yeah.
It's, all of that measuring didn't tell you anything.
The case that this new system is actually at the source, and let's say you know it's an exchangeable sequence, but you don't know the distribution, so you could commit some memory resources to learning what the distribution is, and then thereafter start extracting work from all the sequences that come into the source.
Yeah.
So that would be one way in which your superpowers of measuring degrees of freedom could ultimately benefit you in the long run. So now you can make use of that source and draw work from it.
Yeah, no, I guess that's right. I guess the exchangeable piece didn't work there, isn't it? I mean, if I've got a system that's actually a very long series of states where I have an exchangeability assumption about the states. Actually, I know a huge amount about that system. But of course, it's also true that what I know about the system isn't much good to me if I just have ordinary manipulating cases. So that's nice. That's a nice example of where it really is the case that there's a certain enormous amount of information you could just happen to know in advance about a system that will be useful to you if you have demonic level manipulative powers, and not terribly useful to you if you only have thermal powers. So yeah, that's nice.
And the reason it's good to have a memory device is that although the sequence itself could be used to draw work, if I had to do collective operations on the whole thing, I'd say, well, escape the whole thing in a small subspace of its entirety. So I could just try to extract work, but it's much easier and typically possible to do it one thing at a time. Like, so the operations we can do using one of the systems at a time. So having a bank of memory that allows me to complete a learning process so that I have some good information about it, and then thereafter doing local operations on each system is a sort of practical way of extracting work.
But then I also do worry, if you go and ask yourself, there's this supposed source I've got of exchangeable data, and then if you ask, okay, how does that source work? What's the machinery in that that's doing it? It sort of feels like for that machine to be able to continue producing indefinitely this exchangeable source, then the machine is having to have a big supply of resources of another kind to be able to do that.
Sure.
I mean, suppose maybe the model is something like the device takes cubic centimeters of air at room temperature and prepares, uses its demon powers to prepare that cubic centimeter of air in a very special microstate at the same at the same sort of macro features, and the particular microstate it's preparing is encoded in the memory of the device and I can't get at it. So, and if I know that, then absolutely, of course, I can get energy out that way. But of course, the device had to collect the energy to put it in, because for the device to producing these special exchangeable states, it's got to have some, unless it in turn was just handed on a plate, it's got to have some ability to dissipate an awful lot, to evade an awful lot of memory to be operating that way. I didn't think that's in disagreement with anything you're saying, just filling in the story.